Hello friends, welcome you all to the next lecture of the JCE Connect series of online lectures. We are into module 4 and dealing with the chapter moment of inertia. In previous lectures, we have derived all the relationships for various plane figures for obtaining moment of inertia about the centroidal axis. Then further we have discussed two theorems, parallel axis theorem and perpendicular axis theorem, which also we have used in those derivations. So now from this lecture onwards, let us start with the examples. So before going to the examples, let's one briefly revise the formulas which we will be using. For a rectangle, the moment of inertia about its centroidal x-axis will be BD cube by 12, and about the vertical axis, that is IY, is equal to dB cube by 12. Now one thing you remember here is whichever is the element perpendicular to the axis under consideration, that will be the cube. For example, when you are writing Ix, okay, that is horizontal axis, which will be the perpendicular side, the vertical side, that is depth. So its cube we are taking. Similarly, when we go for calculation of Iy, which axis we are considering? We are considering the vertical axis. So in that case, which will be the perpendicular side, that is B, or width of the rectangle. So its cube we take. So this is the simplest way I feel by which you can remember which cube you have to take. So while calculating Ix, take the cube of depth, while calculating Iy, take the cube of breadth. Now the next figure is a triangle. In case of a triangle, we get the moment of inertia. One is about the base, that is BD cube by 12, IAB, and one is about the axis, okay, that is Ix is equal to dB cube by 36, okay, about the x-axis. Similarly, if you go for Iy, it will be BD cube by 36. So remember that in triangle we are getting two relationships, one with respect to the axis, that is the centroidal axis, Ix and Iy, and one more will be with respect to the base. Then for a circle, as it's a completely symmetrical figure, Ix and Iy will be same, where we get Ix and Iy by the relationship pi r raised to 4 by 4. Moving further, for a semicircle, we get the relationship Ix is equal to 0.11 r raised to 4, where r is the radius, and Iy is equal to pi r raised to 4 divided by 8. Now the thing to be considered here is we may get semicircle in 4 different patterns. So dependingly on the pattern, now here this semicircle which is shown in this figure is symmetrical about which axis? Yes, vertical axis. Means if we cut it vertically, we get two equal halves. So as it is symmetrical about vertical axis, Iy is equal to pi r raised to 4 by 8 and Ix is equal to 0.11 r raised to 4. Now similarly, if the semicircle is in the second and third quadrant, or say in the first and fourth quadrant, that means in that case the semicircle will be symmetrical about horizontal axis. In that case, y will be equal to 0.114 r raised to 4 and Ix will be equal to pi r raised to 4 by 8. So always remember the axis about which the semicircle is symmetrical, that formula will be pi r raised to 4 by 8. Now when you make a list of formulas, okay, I will be expecting you all to draw all the 4 semicircles and accordingly write the formula. For the semicircle which is in first and second quadrant, which is as shown in the figure, these are the formulas. These formulas will remain the same when your semicircle is in third and fourth. Okay, third and fourth quadrant. Whereas for the semicircle which is in first and third and second and fourth, formulas will reverse. Remember, here there will be no minus sign. Okay, even if it is in the other axis, here it is the centroid, because we are just analyzing the figure. Okay, centroid answers won't have any minus sign. Centroid formulas won't come with any negative sign. So next, when we go for a quarter circle, Ix will be equal to Iy is equal to 0.11 r raised to 4 by 2. If we further simplify, we get it as 0.055 into r raised to 4. So we have to deal with 5 formulas, that is a rectangle, a triangle, circle, semicircle and a quarter circle. So these 5 formulas have to be effectively used to solve the examples. The most important thing you have to remember is, just in case of the semicircle, you have to take care of the orientation of the semicircle. When we are dealing with a triangle, we have relationship for the base as well as for the centroidal axis. Circle will remain the same in all the case because it's a pure symmetrical figure. Quarter circle also, in each quadrant, Ix and Iy will be the same, which are given by this formula. So please note down all these formulas properly, so that it will be easy for you all when you start solving the examples. Now, as we developed one table when we were solving CG problems, similarly here we have to develop the table for MI. So the good thing is, more than half of the table is exactly the same, and process also is exactly the same when we do the CG. So if you are perfect with MI examples, that means your CG topic automatically gets covered, or if you are perfect with centroid, 60% of the problem you have covered in that same topic itself. So that's a very good thing about these both units, and hopefully with respect to the internals, you have studied the centroid problems, at least those problems which have been solved. If you have solved them and if you have practiced, MI becomes very easy. So let's take a look at the table which we have to develop. First is comp, means element or serial number or component number. That is the element 1, 2, 3, 4. Next is the term area. That is A1, A2, A3. Next is x, which is the centroidal distance with respect to the selected axis. We will get x1, x2, x3 as we got in the centroid examples. Similarly, y1, y2, y3. So next is a into x and a into y. Up to here, that is column number 6. Everything is same. You need not worry much. Then next part, okay, is what ax square, because moment of inertia definition is square of the distance. Okay, in moment of inertia definition, we have a into square of the distance. So we have to do what? Just a into x square. A value is there, x value is there. That is a1 x1 square, a2 x2 square, a3 x3 square, and so on. How many number of elements you have, those many rows will come. The next column is similarly ay square. Okay, that is a into y. Y will be the again distance. Okay, it's square. So these two columns are also easy. Now next are the most important columns which you have to concentrate on. We are naming it as IGX and IGY. Okay, so even if you refer some other textbooks and all, I request you all to follow one notations only. If you are following any other notes or textbook, follow that notation. If you are completely following my notes and presentations, please follow the same notations everywhere, otherwise it will cause a big confusion. Now what is IGX? IGX is the moment of inertia value about centroidal axis, okay, for one particular element of area A1. Okay, I stands for inertia, G stands for the CG axis, X is the direction. IGX means moment of inertia of individual element, okay, with respect to the axis under consideration. So for example, if I have a rectangle, Igx will be bd cube by 12 and Igy will be db cube by 12. This is individual element. Entire body doesn't come into picture here. Okay, so this is moment of inertia of individual elements, okay, with respect to the axis. Igx means x-axis we are considering, Igy means y-axis we are considering. With respect to x-axis and y-axis, which are those axes? Centroidal axis of the element, okay, centroidal axis of the element. Remember, last two columns are individual element calculation, don't get confused. So this is the table which we will have to generate. Up to ax and ay we have done in centroid. Next things which come in are ax square, ay square, and last two columns become very important. As we go through one or two examples, things will become more and more easy for you all. Okay, so let me brief up the procedure. So firstly, compute the centroidal values of the given figure, x bar and y bar. This thing you know very well. Okay, I did not repeat it. I am confident that you all know this. If you don't know this, practice, then only you can solve moment of inertia examples. So here we have to check what we want, x bar we want, y bar we want, if it is required in further calculation. If the figure is symmetrical directly, can we take x bar and y bar? Remember, this process is same. We are locating x bar and y bar with respect to the reference axis. Okay. Next comes the second part, that is moment of inertia part. Here we, for explanation, we take that 1 1, okay, and 2 2 are the two axes about which we will have to obtain moment of inertia. Okay, 1 1 axis and 2 2 axis. So again I am repeating further, when we go for some examples where these axes are present, we can easily take them. Okay, we will easily get this point. So now when I want to find moment of inertia about 1 1 axis, okay, 1 1 axis will be parallel to your x centroidal axis. Okay, so if you take a figure with your regular axis, the x axis, okay, regular reference x axis, I am naming it as 1 1 because to avoid confusion, already we will have which axis? Centroidal axis, which are x and y. So my horizontal reference axis for moment of inertia problems will be 1 1 and vertical reference axis for moment of inertia problem will be 2 2. Xx will be the horizontal centroidal axis, yy will be the vertical centroidal axis. So now when I take the axis 1 1, how is it? It is parallel to your xx axis. So we apply which theorem? Parallel axis theorem. From parallel axis theorem application we get I11 is equal to summation igx, which we have to take from the column, plus summation ay bar square, which again we will get from the column. So here first we obtain moment of inertia of I11. Then next, again using the parallel axis theorem application, okay, what equation we have? I11 is equal to I bar x minus, sorry, I11 is equal to I bar x plus a into y bar square. Therefore rearranging we get Ix, which is the moment of inertia of the entire body, is equal to moment of inertia about 1 1 minus a. Now this capital A is area of the entire body into y bar square. Now what is y bar? Cg of the entire body, which you have found as with the formula given above on the screen. Okay, so in 1 1 we are using the table. Okay, first step here we are using the table, that is to find I11, and once we come to Ix, okay, we use what? I11 and total area and y bar. So always remember Ixx means with respect to the entire figure, okay, because xx is the centroidal axis of the entire figure, whereas what is 1 1? 1 1 is the reference axis. We use the reference axis for each element, whereas centroidal axis we define with respect to the entire body. Okay, remember this. Again I will repeat, we will use the reference axis with respect to each element, okay, a1, a2, a3, a4. Whereas when we go for Ix calculation, we take x axis, which is with respect to the entire body. So all the things which come in Ix calculation, or say I bar x calculation, we'll keep this notation throughout. I bar x calculation means moment of inertia along x axis of the entire figure. So here we'll get A, capital A is the total area. Okay, capital A is the total area of the body, and y bar square is, here y bar is the centroidal distance of the total body, okay, which we obtained from the above formulas x bar and y bar. So now from this you should be able to write the equation for I22. Okay, so without looking being on this screen only, let's see what can be I22. I22 will be summation of I g y plus summation a x square. Okay, what changes? Instead of x, y comes, instead of y, x comes. That's the only change. Then Iy or I bar y will be equal to I22 minus a remains the same. Instead of y bar square, what we'll get? X bar square. Okay, so this is what we discussed. So again I'm telling, just try to write down these steps, because they will help us when we solve the example, and this will be more clear when we solve one more example. Okay, so things look a bit difficult, but they are not that difficult, because maximum part we have covered already in centroidal problems. It will be only application of Ix and Iy. Okay, so this is the brief procedure for solving the examples. Firstly, we have to make the table. 60 to 70% of the table is the common, as we have done in CG. Extra columns will be ax square, ay square, then igx and igy. Igx and igy represent the individual moment of inertias of the element. Okay, so then we apply parallaxis theorem and we get Ix and Iy. In some given examples, if directly the centroidal axis is given, there is no need of I11 and I22. Directly we can go for Ix and Iy. So again I am repeating, we will go through some examples and then this concept will be much more clear. Thank you.